Good evening. Hope you're able to hear me. So we'll start. We'll. I don't think it's. We can't wait for other people, so we'll start, and then let others join in the meantime. So hope you're having a good evening. Okay. So I'll be sharing the PowerPoint. Just a moment. Can you see this? Welcome to the week 5 problem solving session of the course Natural Hazards. I'm Anjana, the PMRFTA. So, since till this, like last week, since I have discussed uh, till your week 5 sessions, so I thought I will. Okay. So since I have discussed all the theoretical part and certain problems till week 5 in the last session, so I thought I'll do a small recap so that you don't forget the things you have learned till now. So this is like, I think you've got your week 6 videos. So I think it would be better before that you just have a small recap of all the things that you've learned till now. So I'm just doing this in the form of certain questions and answers so that it's easier for you to understand like where that particular concept is being used and how. So I can also focus on the way it is like how you reach to the answer and all those things. So let me begin. So this is a recap, so I think this will help you out for your exam also. So the first question is seismic zonation dash is designated to Himalayan mountain belt and the most devastating earthquake till date in this region was. So this is from your assignment. So since you might have submitted it, so you can give me the answer. Any one of you, just like you know how many like seismic zonation is, right? There in India. You can give me any answer. It doesn't matter. Like today I was thinking like I'll focus on these questions and answers so that if you have any difficulty with these, then it would be better. Then next week we can go on with the volcano part, which is your week 6 lecture. Seismic zonation is like a particular number is designated to the Himalayan mountain belt. Like this is something you should know. The other one, okay, that's fine. That's more of a general question. But the seismic zonation, I had shown you these maps, seismic zonation maps. So please try to recollect, or you can just make a guess also, like anything. Just give me an answer. Okay, so seismic zonation. I hope the question is clear to you. So, like seismic zonation is basically. I'll just yeah. So if you look at this, like seismic is basically it is related to the earthquake, and zonation is since our country is very diverse, like the tectonically or any other parameters. Like there are stable areas, there are unstable areas. So accordingly, like our Indian subcontinent that is divided into certain zones, and how they are divided, that is based on their seismicity. Like the region which is more prone to earthquakes, we put it as zone 5, and those which are not that much prone to earthquake, like on a moderate level or even a minimum level, we call it as zone 1, zone 2, not zone 1. So we have zone 2, zone 3, zone 4, and zone 5. So if you remember, the Himalayan mountain belt, that is a very seismically active area. Like it is very much prone to earthquakes. So recently we have these uh, earthquakes in the Nepal region. So that is very close to, like that is a part of this Himalayan mountain belt. So since this region is very much prone to earthquakes, so then the seismic zonation will be 5 for this area. So that is how the answer will come. So this is 5, and the most devastating earthquake till date in this region was, that is the Assam earthquake, I think. Yeah, the 1950 Assam earthquake. So this diagram is itself clear, like makes it clear to you. So you can see, like if you look over here, you can see zone 2, zone 3, zone 4, zone 5. So zone 2 is least active, zone 3 is moderate, zone 4 is high, and zone 5 is highest. So the highest one you can see in this part, that is the like the Kutch region. Then the you can see, like this is kind of like in fragment form, but then you can see zone 5 and zone 4. So that is along this entire region, plus the Andaman and Nicobar Islands. So it's also part of India. So that's how the answer is coming. So even if you don't know this one, like it's good for knowledge that 1950 Assam earthquake is the devastating one till date, but then you should be having an idea regarding seismic zonation. So moving on to the next question. Uh, the Kutch mainland fault and the South Wagad fault dip in dash dash respectively. So I'm asking the direction, okay. Uh, so in which direction in terms of east, west, north, south, that way, and that is dash to each other. Like how are they placed, or like their positioning, how they are. So like Professor Malik has discussed this in your last week 5 lecture, yeah, week 5 lecture, he has discussed this Kutch region. So this he has mentioned. So dip is mainly in which direction it is inclined. So like if you have uh, let's say, of course the surface of earth is not so perfect, but then for your understanding, a three-dimensional diagram if we draw, and if we consider an inclined section like this. So you have to imagine that this is a box, and that inside the box there is a sloping part like this. So the angle of dip will be, like dip is basically how much inclination it has to this horizontal surface. So this will be your angle of dip, and the direction in which it is dipping, that is your like dipping direction. So that is what the question is, the Kutch mainland fault and the South Wagad fault. So they have, of course, the fault is at like fault plane is at an angle. So in which angle and in which direction it is, not angle, in which direction it is dipping, and how they with respect to each other, how they are positioned, that is the question. So, like, you have an answer for this, or like, should I explain? Okay, so I guess you might have done this because this was last week's assignment, but I thought I'll start with this. Yeah, the answer is, yeah, you're right. So it is south, north, and it is opposite. So in this diagram itself, you can see this is the Kutch mainland fault, and this is the South Wagad fault. So in from this itself, you can like if I draw it here, you can see it's somewhat like this. So this is in this direction, and this is in the other direction. So they are opposite to each other. And in terms of the location, So it is dipping south and this is dipping north. So if you look at the latitude, you can see this is going a little upwards, so that is north, and then this is a bit towards the uh, uh, bot, uh, bottom part, so that is like south. Seismic microzonation is done on the basis of computed dash, which in turn depends on lithology of the area. So you know like very well what seismic zonation is. Okay, so seismic zonation on a large scale, if you look at the previous slide, so you see this is the Indian like our map, right? So in a broad classification is what seismic zonation does. So it doesn't take into account every tiny little place, but rather it is taking into consideration a large area. So on basis of that, it is creating these zones 2, 3, 4, and 5. But what you have to understand is even within these regions, there will be regions which will be more prone to that seismicity, like effect of that seismicity, and another region which is not that much prone to the seismicity. Therefore, although we have a seismic zonation, with respect to each place, its lithology and certain characteristics, that region is again, you know, again zoned into small, small pieces. So that is like microzonation. So in this case, uh, that microzonation, like how they have to create the zone, that is computed based on a particular thing. Okay, and that particular thing depends on the lithology of the area. Lithology is like what kind of rock or like sediment is in that region. So whether it is hard, whether it is soft. So what is that like, on the basis of what do you compute it? Any idea? Like I had mentioned this in the last lecture also, like a problem solving session. There is a particular feature or a characteristic of uh, like of that lithology in a particular region, based on which the effect of earthquake can be more pronounced or less pronounced. So can you make a guess? Okay, so the answer is peak ground acceleration. So that measures, it's a measure of how much the earth shakes at a given geographic point. So this is basically, the idea is, if this region, let's say if we take this Gujarat region. So this region is broadly classified in terms of zone 3, 4, and 5. Okay. However, if you take the zone 5 itself, there will be regions in which peak ground acceleration will be more, and there will be regions where peak ground acceleration will be less. So, depending on that, like that peak ground acceleration will depend on the lithology of the area. So, if it is uh, soft material, okay, any soft material is there, then the peak ground acceleration will be high. And if the material is like a hard rock, or if something which is more consolidated, then that itself will dissipate that energy. So that material itself will dissipate the earthquake energy. So the effect of that shaking will be less. So based on this peak ground acceleration, we are uh, doing the seismic microzonation at a given geographic point. So this, if you remember, I had discussed about this Mercalli scale. So this is the instrumental intensity. So if you have an intensity, say 1, like that is how you're characterizing it, then its ground acceleration is very, very less. on this around this number. Velocity is also less, so this shaking which occurs during an earthquake is not felt, and as a result the damage is also less. But as you come to, let's say, 6, so you can see it is bold, they've kept it in bold letters, so that you can see the number has increased, the velocity has increased, the strong shaking is experienced, and the damage, however, is not very high. Although shaking is there, the structures can withstand. However, when you go to like 9 or 10, you can see this number, not only this numbers have increased, you can see the perceived shaking is in the range of violent to extreme, and the potential damage is heavy to very heavy. So, in some regions, people say like they barely felt the earthquake, and in some region, that shaking. That's why I said like you have to keep in mind that seismic microzonation is further done, because sometimes the intent, even if the magnitude of that earthquake is moderate, at times what happens is that because of the lithology of the area, that effect might be more. uh, Structures might fail, so all these things needs to be taken into account when it comes to seismic microzonation. I hope that's clear. So this brings us to the next question. Dash is a section with the no earthquakes have been observed historically, but it is believed that the fault segment is capable of producing earthquakes on the basis of ongoing deformation computed from GPS. So this also I had discussed. So there is, have a term for a section in an area with no earthquakes in the near, like on a historic basis. If they see, like there might be certain regions which did not experience earthquake for a long time, but its adjacent regions have experienced. So such small sections might be there in a area. So what do you call that section which did not experience any earthquake historically, but then it is capable of having an earthquake in the future because it is still uh, you know undergoing deformation? What is the name of that section? Just try to recollect, like it is related to earthquake, and there is a section which is missing, so at least from that keywords earthquake and something is missing, so how do you coin a word for this section? When it is earthquake related, we largely say in terms of seismicity, right? So just try to recollect, like I had mentioned this also, and in the lectures also sir has mentioned. So and you have done this assignment, so please make a guess or please put your answer. Yeah, as Zafirul Islam has written, the answer is seismic gap. So that's what I was saying. So seismic is something related to earthquake, and gap is which was missing, right? So this diagram also I had shown. So this is a seismic gap. Uh, that is the two purple rectangles in the historic earthquake pattern along the San Andreas Fault south of San Francisco. It was filled in 1989 by the Loma Prieta earthquake and aftershocks. So, if you remember, this San Andreas fault, it is a transform fault. So, there is basically horizontal movement is happening. Okay, this is a transform plate boundary, you can say. So, in the San Andreas fault, uh, it's a very long fault. So, because of which people observed, or the scientists, they observed that in this particular region, which is the purple region, like no earthquake had taken place for a long time. But then in 1989, that region was also experienced an earthquake, thus filling the entire length. So that is why we call it as a seismic gap. Or in India's example, also I think sir had shown somewhere in the that Himalayan belt he had shown. So if we consider this region, like let's say this is the okay, so in some places there was earthquake, but then in this region for a long period earthquake was not seen. Then in this region earthquake was there. Again in this region earthquake was not seen for a long time. Just because these regions didn't experience an earthquake, that doesn't mean that it will never experience one. Rather, you have to understand that since it's in a seismically active area, at one point of time, this region will definitely uh, experience an earthquake because of the ongoing deformation. Like the fault is still moving. So, let's say if it is a reverse fault, so the hanging wall is moving up, so that movement is still there. Only thing is at what point that the stress, that built up stress is going to break, and in the form of an earthquake. So it might take some time, but then these regions are at as much risk as the adjacent regions for an earthquake. So the earthquake occur in the dash segment of the collision blocks of Eurasian and Indian plates. So you know the Indian plate is pushing against the Eurasian plate. So where does the earthquake happen? Like we know that where that plate boundary is, where you have the Himalayas, that is a very seismically active region. So where in that in those faults does this earthquake occur? Which segment of the collision blocks? Okay, so the answer is brittle locked. So if you remember this diagram, you can remember that with increasing stress. So normally rocks, if you think, you know that they are hard, but then each kind of rock has some limit. Okay, so elastic limit is there, brittle failure is there. So when you subject a rock to a lot of stress and strain, stress is like the force, and the strain is the reaction to that force applied, that you can say. So with increasing stress a rock deforms elastically, then plastically, before ultimately failing or breaking in an earthquake. A completely brittle rock fails at its elastic limit. So that what they're saying is, let's say you have a rock which has some amount of elasticity within it. Okay, so like it can tolerate a particular amount of stress. So let's say this particular rock, it can tolerate that stress till here. The elastic limit is till here. So till here, till this much of stress, like till this much of stress, this rock can, like there is a possibility that when you remove the stress, that rock can go back to its previous state, like how it was. So that is a reversible thing. However, what happens is sometimes when the stress and the strain accompanying it, if it exceeds this elastic limit, so then what happens is plastic deformation happens. So some kind of change will happen in the rock which is not reversible. Like that deformation will be visible. It can be in the form of change in the minerals present in the rock. It can be due to the change in the structure of the rock, whatever it is. After once it crosses the elastic limit, plastic deformation happens, and that is not reversible. You'll not get back the same exact rock which was there in the initial state. And then if you still increase the stress and the strain, what happens at one point, this plastic deformation will happen, but then when it reaches the brittle failure, that fault will slip and the earthquake will happen. So in terms of earthquake, what is happening is, let's say this is uh, a reverse fault. Okay, so the hanging wall is moving up. The foot, we normally denote it like this. So the foot wall is here. So with respect to that, this is moving up, and this is our fault plane. Okay, so let's consider this point. uh, this is our point, and this is a cross sectional image, so you have to imagine that this entire thing is a plane. Okay, so if I draw it in a three-dimensional manner, so this is how it will be. So this entire plane is sliding, that hanging wall is sliding in that plane area. So what happens is, let's say if we consider this point, so that point is basically along this region. Okay, so there will be different kind of rocks. Obviously we know that this hanging wall, footwall, whatever we are seeing, that is based on some rock, and then there is a weak point, right? So those rocks along this region, it is being subjected to, this is the brittle locked point. So this region, stress and strain is accumulating, it is not able to move up as easily. So once it is locked over here, first elastic deformation will happen, and once elastic limit is crossed, plastic deformation will happen, where it cannot go back to its initial state. And then when the brittle failure happens, like the maximum possible stress accumulation is there, then the fault will slip, it will move, and as a result an earthquake occurs. So we say this such segment of the collision blocks as the brittle locked segment, where the uh, final movement happens. I hope that's clear. So moving on to the next question. The dash is the dash dipping fault that holds the epicentral location of the 1819 earthquake. This is a very general question. But yeah, still, if you can give it a try, since it was part of your recent assignment. Yeah. So I say, put it in the chat. The answer is Alaband fault in, yeah, and that is a north dipping fault. So I hope you guys are clear with this dipping direction and all. If you have any doubt, you can stop me and ask. But I had mentioned it in the first or second question. So the Alaband fault, 1819. So I'm just giving you an idea of what happened. Like Professor Malik has also said, but then I thought, since the question is there, I'll just briefly touch upon that. So the 1819 Ran of Kutch earthquake. So Ran of Kutch is in Gujarat. So 1819 Ran of Kutch earthquake. What happened, and like how this Alaband fault, all those things I'll be discussing. So the magnitude was 7.7 to 8.2. So you have to understand how large that is, and then how much of effect it might have had on that particular area. So the intensity based on the Mercalli scale was 11, which is very extreme. Okay, so this is not, I don't think this is the based on the modified Mercalli scale. This might be based on the initial one. So either way, you have to understand magnitude is very high, intensity is very high. So definitely the effects of earthquake is felt, right? So what happened is this even triggered a tsunami. So you know the Sumatra earthquake triggered a tsunami in December 2004. So similarly, this Ran of Kutch earthquake uh, in 1819, that triggered a tsunami. So I'm just going point by point. So we know a high magnitude, high intensity earthquake happened, which triggered a tsunami, and what all things happened. So this resulted in Sindri Lake. Okay, Sindri Lake formation. So Sindri Lake is an area of subsidence. So subsidence is basically, uh, due to the overlying load, or because of this movement along the fault, subsidence is basically some depression kind of structure forms, and that uh, led to the formation of Sindri Lake. So that was one thing that formed, and the other thing that formed was the Allah Bund, or the Dam of God. That is the name, Allah Bund or Dam of God. So this is a local zone of uplift to the north, about 80-kilometer long, 6-kilometer wide, and 6-meter high, that dammed the Puran or Nara river. So why it is called the Bund, Allah Bund fault, is because it acted like a uh, like bund is basically a damming structure. So what happened during the earthquake, uh, that slip along the fault resulted in a region of upliftment. So a particular region, let's say, if you remember the diagram, so this region got uplifted, so this came up, and the Nara river was coming, and this acted like a dam for that river. So that's why you call it as Allah Bund fault or the dam of God. So the two structures that formed as a result of the 1819 Ran of Kutch earthquake are the Sindri Lake and the Allaban or Dam of God. So this, I don't know how your exam questions might be, but this is something you can keep in your mind, because this is something which sir had discussed. So if they ask you like what kind of features, or like what was characteristic of the 1819 Ran of Kutch earthquake, you can very well say that it was a high magnitude earthquake, it was of large intensity, it triggered a tsunami, and also it resulted in the formation of Sindri Lake, which is an area of subsidence, and the Allah Bund or Dam of God, which was a region of upliftment or a local zone of uplift, which acted as a dam or a bund for the Puran or Nara river. This is just basic facts, but if you have such questions in your exam, you can very well write these points. So this is a diagram. So you have the Lake Sindri over here, and this is the Allaban fault. So the hanging wall was going up, and the footwall, like with respect to the footwall. So this is the scarp. Scarp is basically the exposed region of, like once that movement happens, we call it as fault scarp. In this particular case, that is the Allaban scarp. So scarp is basically the region which is exposed, a region or that part of the fault plane which is exposed on the surface as a result of fault movement. And this is, as a result of this movement, this region got uplifted and this region experienced the subsidence. So in that subsidence, the Sindri Lake formed, and over here you have the Allaban scarp. So I hope that is clear. So this brings us to the next question. This phenomenon is known as dash. This will result into increase in pore water pressure and result into formation of sand boils. So this I have told multiple times in the last two sessions, and also I have shown you videos regarding this. So can you just tell me what phenomena is a result of increase in pore water pressure and that results in the formation of sand boils? This was from the earthquake part. So try to remember. We had few questions also related to this in the last session. So yeah. So it is densification and liquefaction. Okay. So more or less it's the same thing. The idea is when the pore water pressure increases, so the material like sand or silt, which is not very, uh, which cannot hold together that well. So what happens is it will move apart. It kind of liquefies, and then it either it can just come out and move, or in the form of sand boils, or it can lead to another feature. If you remember, like if it comes out, you call it a sand boil. Do you know what is the other feature that is as a consequence of liquefaction, in which you have this blocks of land, like broken blocks of land? I think I have a question on that also in the upcoming slides, but I was just asking since we were talking about this. Okay, I think we'll touch upon it when the question comes. So, yeah, this, I think I have shown you this video, but still, just to recap. So, saturated, cohesionless soils. So, cohesion is basically the ability to remain consolidated, like stick to each other. So if you think of clay, the sticky mud or clay, that can hold water for a long period of time, and the water, like, it basically absorbs the water. But cohesionless sand or silt, cohesionless means the for example, if you go to the beach, so unlike the clay, that even wet sand will also not remain very close to each other, rather it will be in a liquefied form. So that's why they are saying that. So you can see the blocks, right? How the road has broken. So the entire structure is collapsing if you look at that. Okay, so that's it. So I just showed it again, like I had shown it in the week before, or last week. I don't remember, but I had shown this video, but I just showed you again so that that visual memory is there. So you can see, in certain cases the structures have entirely collapsed into the it has basically that sinking you can see of the entire structure. So normally, either you should not build like before building um, a structure in a particular area, be it dam, which is at a large scale, or be it a building, which is not as big, but still, if you're making something, that's why in civil engineers, they basically assess the area before any construction. Like their opinion needs to be taken into consideration. A geologist needs to see the area, especially if it is a seismically active area. So you need to see, but then there are certain situations which are inevitable, like you have to build the structure because you don't have any other place. uh, in such cases, structures are built in such a way that they can withstand that entire movement and even this like all the effects of the earthquake. So this is again a small video which I had shown you regarding sand blows or sand boils. So this is the real life like picture. Now they will just cut this portion as a cross section and show you what is happening inside. So you can see silt is there, which is a cohesionless material. Then in between clay is there, which has cohesion, and then you have sand at the bottom. So that sand is liquefying, and somehow it is cutting through the weak zones and coming on top. So that is the animated part, and this one is the one which you actually see. That, like, this is the Loma Prieta, like sand lows, which formed due to the Loma Prieta earthquake. So Loma Prieta earthquake is a good example of seismic gap, if you remember from the previous slide. So the next question, a large portion of the Mexico City sits on the bed of dash since European settlements way back in 1520. This example is a bit important. I will, like, once you give me the answer, I'll tell you why. So, a large portion of the Mexico City sits on the bed of dash, like where, yeah. So, as Anandraj has said, it is a lake deposit. So, this is important because the modern Mexico City, which you have, it was built by the Spanish over the ruins of the Aztec capital of Tenochtitlan. So, what happened is that, as I said, like they needed an area. So, what they did, uh, they drained that entire lake uh, over centuries, and they expanded the Mexico City. So first it was in on an island in the Lake Texcoco, but then gradually, in order to expand the city, they drained the lake. However, you have to remember, wherever you have a river bed, you have a lake bed, you will have such soft material, right? So at present, much of the city, it stands on layers of sand and clay. So sand is there, clay is there. So you know how much like peak ground acceleration will be, right? And these soft water laden sediments make the city vulnerable to earthquakes. So such a setting can amplify the seismic waves to be 100 times stronger than usual. So even if like normally, let's say you have two places. One is this Mexico City, like which is like that portion on the lake bed, and then you have a adjacent place which is not on the lake bed. So the same magnitude earthquake in both the regions, the effect will be more pronounced in the Mexico City. So the reason is that that city is standing on a layer of sand and clay, and they are very soft water laden sediments. Like water can clay will take in the water, and sand like when water is there, the sand pore water pressure increases, and you know what happens, right? The densification, liquefaction, all those things. So because you have such soft material over there, even if the magnitude of earthquake is same, the effect of that seismic wave, like that seismic wave will be amplified furthermore in this region, so 100 times more. So the effect will be felt more in the Mexico City. That's why this example is important. Okay, if you have a descriptive answer or something, and if they're asking you about the influence of lithology on the earthquake, effect of earthquake or something like that, then this is a good example. You can give a good example, right? That the example is what? A portion of the Mexico City which is standing on a lake bed. So, a devastating earthquake in 1985 killed about 10,000 people, had an epicenter location nearly 400 kilometers away from Mexico City. So, you have to imagine that epicenter was not even very close by. So, as you move further away from the epicenter, the effect will be comparatively less. So, 400 kilometer is not a small distance. Even then, because that region is such, like the condition is such, uh, that earthquake led to the death of almost 10,000 people, and they suffered a lot of damage. So this is a very good example. I mean, you don't have to explain all these things like how that was built. I just said it for your information. But if you are asked about an example, or like if you are discussing about the importance of lithology and earthquake with respect to earthquake, then this is a very good example. A coupling value of dash means the area is fully locked, while a value of dash means that it is fully creeping. Creeping is like slow movement. So, if you know the answer, give me the answer, or else I can give a brief explanation. Yeah. So, as Anantaraj has given, the answer is 1 and 0. So, the coupling value or the coupling coefficient of 0, it indicates that the fault is creeping at its long term rate, whereas a value of 1 indicates that it is fully locked and thus accumulating strain energy that will be released in future earthquakes or episodic creep. So it's kind of like quantifying how the stress and strain is accumulating. So this is how it is calculated. So you can see this is C is basically the coupling coefficient, and the V0 is the plate convergence rate, like uh, how much fast or slow it is moving, converging, and V is the slip rate, how much that slip is happening. So the plate is moving, at the same time that slip can also happen along the fall plane. So all those things are considered for the coupling coefficient, and then they are saying if it is 0, if this value is 0, that means the fault is creeping, that is, it is moving. So if it is slowly moving, then there is no risk, but the problem happens when that movement is restricted. So 1 indicates that that movement is like restricted and that fault is fully locked. So the strain energy is further getting accumulated. So you have to, if I can say analogy, like let's say you are angry with somebody. So that anger, if you don't talk to them, like let's say you have a friend and you're angry with them, and if you don't tell them you're angry and that anger is building up inside you, that is not good for you and neither good for your friend. So that is like that much of pressure is getting built up inside you. You are, because of that anger, you are not able to do anything. And then at one fine day, that for a small thing itself, your anger might burst, you might get more angry with the person. So it's kind of like that. So if it is slowly moving, like then it is fine. But then if it is locked, which is basically C equal to 1, then that accumulated energy will be released in the form of an earthquake. Indo-Gangetic, it's not plans, it is plains, is the region beyond dash, that is the dash thrust belt of Himalaya. So I had shown you a cross section in the last class, having this Himalayan frontal thrust, main boundary thrust, main central thrust, a small cross section I had shown. So in that, beyond what is the Indo-Gangetic plains, and like any answer? Till this, it is basically from your assignment. So I deliberately kept it like that so that it will be a good revision. So that is the Himalayan frontal thrust, and it is the youngest thrust belt of Himalaya. So it formed on at a later stage. So if you take a look at this diagram, you can see, right? So this is the Indo-Gangetic plain. So this is the main frontal thrust, or it can also be called as the Himalayan frontal thrust. So that is the one. Okay, this is the one. MBT. Like major ones are these three. Other ones are also there, but this is the main one. So main boundary thrust is there between the sub-Himalaya and the Indo-Gangetic plain. Like MFT. Then you have the lesser Himalaya between the main central thrust and main boundary thrust. And beyond that, you have the higher Himalaya. So such, you don't need this detailed explanation, but you just need to have an idea. So that till then I had discussed from the previous week's assignment. So now we'll be covering some other questions from week 1 till week 5. So which of the following activities is covered by disaster management before, during, or after a disaster? So you need to recollect disaster management. One diagram was there, one circular one. So what all following okay, the following activities: reconstruction and rehabilitation, mitigation and emergency response, and all of the above. What is the answer? Yeah. So the answer is all of the above. So you have to remember disaster management is basically how well you are going to like you're prepared for the any kind of disaster before it strikes. So before is basically being prepared, or prepared for a disaster. So then during and after. So during is how emergency response, like how quickly you are going to prepare to respond, that is there. Then reconstruction and rehabilitation happens after. Mitigation measures is also very important. It's basically the idea of disaster management is you cannot avoid the natural hazard or disaster from happening, but you can make sure the complications or the casualties associated with can be reduced if you have a proper disaster management plan. So this is from the week 1. So I'm just recapping everything. Tsunamis is coined from Japanese dictionary, which means harbor waves generated by what? So we have the options: earthquakes, volcanic eruptions, underwater slides, landslides, and all of the above. Like what all? Yeah. So the answer is all of the above. So tsunami can be generated because of a earthquake. We have a very good example. Just recently, I talked about the run of Kutch 1819 earthquake. That is an example. Then the 2004 Sumatra earthquake also resulted in a tsunami. So that is there. Then volcanic eruption. I think I can't pinpoint an example right now, but yes, underwater volcanic eruptions or even I don't remember the name, but just recently, like one or a few years back, uh, because of a volcanic eruption, an entire part of the volcano's that side it collapsed. So it kind of slid down into the ocean, and because such a huge amount of material all of a sudden it came, that resulted in a tsunami. So all these things can be like tsunami as such doesn't happen. It is happening as a consequence of all of the above: earthquake, volcanic eruption, and underwater landslides. The evidence of seafloor spreading, which explains the drifting of plates at mid oceanic ridges, comes from what? So the options are fossils in South America and Africa, magnetic minerals on the ocean floor, the breakup of Pangea, and the ancient climatic conditions. For this, you have to understand what seafloor spreading is, where it is happening, and then like how people understood or what was the evidence for that. Okay, and any other answer is there? Like Anand Raj has said, it is ancient climate condition. So any other answer? Okay, so before this, you have to, like, you might already know, but I'm just telling this. So let's say this, okay, breakup of Pangea. So you have to understand this breakup of Pangea, all those things, that is not, you can't say it is a direct evidence or anything, because you have to focus on these two keywords: seafloor spreading and mid-oceanic ridges. So you have to see, let's say this is a mid-oceanic ridge. So mid-oceanic ridge is the region, it's a divergent part in the ocean floor. Okay, so where this plate is moving in this direction and this plate is moving in this direction. So when they are moving apart, or let's say you have a single, you have a paper like this, okay, and you pull it from this side and you pull it from this side. So most of the time it will break around somewhere in the center or maybe a bit off, but still it will break, right? So that similar thing is happening over here. So this one is moving in this direction, this one is moving in this direction. So you have two plates over here. So what happens is that the earth's like below the crust you have what? You have magma, right? In the mantle region you have magma. So what happens is that if you have a magma upwelling, something like this. So what happens is, once you have this gap coming, so the magma which is below it, that will come up and it will go down the sides like this. So what happens is, this keeps on happening. So like, it cools, and that's how we say the ocean floor, it is constantly renewed and replenished. Like, it is destroyed, and again, because it is breaking apart, it is destroyed, but then it is immediately uh, replenished also. So that's why usually people say oceanic crust, when compared to continental crust, is more younger, like around 200 million years, you can say. But then continental crust, like we have evidence of like 4 billion years ago and all. So that's a different story anyway. So the magma is coming out, and it kind of solidifies on either side like this. So that's how the ocean floor is built. So what they're saying is, the evidence of this particular phenomena, that sea floor is spreading out, that in the, especially in the mid-oceanic regions, that came from the study of magnetic minerals on the ocean floor. They did paleomagnetic studies. Paleomagnetic, so paleo is past, magnetic study is, what they did is, they took samples from these entire section, like small samples, or they they can even do this, not physically, but they can do it with instruments also. Like, I'm not very well versed in that thing, but anyway, what they did is, they studied the minerals which are present in this material which has solidified. So what they saw is that magnetic minerals, like iron rich minerals, all those things, they were present, and they had this particular, uh, for a particular time period, they had one particular alignment, and then for the next another. So I'm not going into the detail, but uh, essentially what they understood, like what the scientists understood, is the sea floor is not staying intact, rather it is spreading out. So that idea was, like, they got it from the studying the magnetic minerals on the ocean floor. When you talk about breakup of Pangea, or the fossils in South America, Africa, that is basically giving you the idea that once we had a supercontinent, and then because of the breakup, of that supercontinent to multiple fragments, we have the continents as of now. So those are evidence for that, and for the sea floor spreading, the evidence is magnetic minerals on the ocean floor. The next question is, earthquakes and volcanism are a dash that threatens or acts hazardously in a defined space and time. So you have the options as endogenic process, anthropogenic process, exogenic process, none of the above. So we have discussed. Okay. Any other answer? Okay. So this was from the beginning, week 1 part. So you have to understand what endogenic process is, what anthropogenic process is, and what exogenic process is. That will give you the answer for this. So endogenic process. So endo means something is happening inside. So that is all those processes which happen inside of the earth, we call it as endogenic process. Anthropogenic process, anthropogenic is basically human influenced processes, like anthropocene means the time period in which humans are exerting an influence. So anthropogenic is related to human beings. Exogenic process are all those processes which take place on the outer part of the earth's crust. So earthquake and volcanism, as much as we have discussed till now, earthquake is happening. Why? Because of the slip, or the accumulated stress in the fault plane, and that is happening inside of the earth. So that is one thing. So, and then volcanism, if you see, you have a volcanic mountain on the outside, but the entire magma and all those process, that is actually happening inside the earth. So as Zafirul has put in the chat, so the answer is endogenic process. So it is happening inside the earth. So earthquake and volcanism are endogenic processes which threatens or acts hazardously in a defined space and time. Next question. When two tectonic plates move away from each other, then those are called dash plate margins. This is a very easy question. You can just give me the answer even if I don't show you the options. We had discussed this multiple times. You had a question similar to this in your assignment also. What will happen, or what do you call? Yeah. So the options were destructive, transform, constructive, none of the above, and as Zafirul has put, the answer is constructive. So that's the same example which I gave in that seafloor spreading thing. So you know something is getting constructed, right? That seafloor is not getting destroyed. Constantly, some material is being added to it. But in other cases where you have, can you tell me what is an example of destructive plate margin? Like constructive plate margin, we have the mid-oceanic ridges, right? So similarly for destructive plate margin, what do you have? It's not essentially continental. When you say mid-oceanic ridge, that is like two plates are moving away and something is formed, and that region we call it as mid-oceanic ridge. An example of destructive plate margin is the subduction or collisional plate boundaries, okay, or plate margins. So a good example of this is subduction. Let's say we have a good example in the Andaman region, and collisional. A very good example is the Himalayas, which you can always remember. So how does this happen? So if you I should have put a good image, but I'll somehow draw and show you. So let's say this is a continental part, okay? So this is continental crust. I'm marking it as CC. And then adjacent to it, you have the oceanic crust. So that is OC. Okay. So this oceanic crust, that is, uh, more dense when compared to continental crust, although oceanic crust is what? It is thinner, okay? Like continental crust is thick, like around average is 35 to 40 kilometer thick. Compared to that, oceanic crust is, I think, not much, maybe 7 to 10 or something like that. Either way, although thickness is less for oceanic crust, it is denser. So because its density is high, when continental crust is moving and oceanic crust is moving towards each other, the oceanic crust will go down. Okay. Similarly, let's say you have a continental crust on this side. So this part of the oceanic crust is going down in this side. So essentially what is happening? This side is going here and this side is going here. So there will be a point. So here we have subduction. Okay, so this process is subduction. Then this will again come closer and there will be a time when this entire oceanic crust has subducted beneath this and this continental crust, and then these two continental crust will meet. Okay, so the entire subduction has happened and then continental crust comes together. So when this happens, most of the time the continental crust has comparable density, like that there is no large density difference. So because of which, instead of one plate going down the other, what will happen is that they will collide. Just like how let's say two cars moving fast towards each other, they collide. Similarly, of course, this here, it's not very fast, it's a very small scale movement, but then the continental crust will collide, and then it will result in the formation of this mountain chain like Himalaya. I think Alpine mountain chain is there. So all those things, Andes. A system which can exchange energy with its surroundings but not the matter is termed as. We have different, mainly three types of systems. So out of that, what is the name of that system which can exchange energy with its surroundings but it cannot exchange matter? Just this is all like I'm keeping these questions so that you can recollect from the past weeks, so that when your exam comes it will not feel like it's very new to you. There are three types of systems, right? Can you give me the names of those systems? Okay, so I'm giving you the option. So you have open system, you have isolated system, you have closed system, both isolated and closed system. So out of this, which is the system that can exchange energy but not matter? Yeah. So the answer is closed system. So open system, as the name itself tells you, it exchanges both matter and both energy. So if you keep a glass of water, a hot water glass somewhere, and it is left open, then after some time, that like it will cool down. That hot water will cool down. If it is isolated system, it will not share, like exchange neither energy nor matter. Then closed system is where you have an exchange of energy. So let's say you have a flask in which you are keeping some hot coffee. So that hot coffee will remain a hot coffee. No, that is for the isolated system. In case of closed system, if you just have a hot coffee in a tumbler or something like that, which is closed, but then that energy will be exchanged, but the coffee amount will more or less remain same. The next question is, in a cyclone, the direction of circulation is anti-clockwise in the northern hemisphere and clockwise in the southern hemisphere due to a particular thing. What is that? Cyclone is a region of intense low pressure, right? And some movement is happening. So that direction of circulation is anti-clockwise in the northern hemisphere and clockwise in the southern hemisphere. Why is that so? Like there is a term for that. I can give you the options. I'll see. Yeah. So we have the gravitational force, Coriolis effect, inclination of Earth's rotational axis, none of the above. Okay. Yeah. So Zafirul has given the right answer. So the answer is Coriolis effect. So if you, for those of you who know, this will be a revision, but for those who don't, just please pay attention. So let's say this is our Earth. Okay. So, and we know we have the equator over here. Okay, this is the equator. So the idea of Coriolis effect is that if you are standing on the equator facing towards north, this is north and this is south. So this is your northern hemisphere, this entire thing, and this is your southern hemisphere. So if you're standing on the equator, you're facing north, you're looking towards north, and you're throwing a ball from, let's say, point A to point B. Okay, this is your intention, like you want to throw it like this. But because of this Coriolis effect, what will happen is that the ball will not go straight, rather in the northern hemisphere it will go to the right. So with respect to your position, it is going to your right. So your intention was to throw from this point to here, but the ball, if you throw it from here, it is going to go in this direction. This is one of the reason is the rotation of the earth about its axis. Similarly, if you are standing on the equator and you're looking towards the southern side, okay, so you are standing here, so you are throwing a ball from here. Your intention is to throw it from here to here, but it is going to go in this direction. So here you have the motion like this. No, I'm sorry, it is going to go in this direction. Okay, that was my mistake. It will go to the left in the southern hemisphere and to the right in the northern hemisphere. So that dictates like in what pattern that circulation is going to be in the northern hemisphere and the southern hemisphere. So only thing you have to keep in mind is because of Coriolis effect, the circulation is going to be anti-clockwise in the northern hemisphere. So that is, in the northern hemisphere it will be anti-clockwise, and in the southern hemisphere it will be clockwise, like this. So the dash region records around 70% of the world's earthquake, measuring up to magnitude 7 or more. So this I'm asking with respect to the entire, the world map, if it comes to your mind. So in that there is a particular region which will record around 70% of the world's earthquake. What is that region? I had asked this question in the session, like our problem solving session also, previous one. But this is a bit important, I felt, so that's why I'm asking again. Any idea? Which region in the, like in the world map, if you see, you can recollect the map that I had shown also, in which you have that plate boundaries, the earthquake, volcanoes and all. If you remember, I had shown you two world maps with that image. So what do you call that region as? I'm giving you the options here: Asia Pacific, South America Pacific, Europe Atlantic, Africa Indian Ocean. Yeah, you have given me the answer. 1 second. Yeah, the answer is Asia Pacific. So if you remember, you'll also remember the side of where you have this uh, South America, North America, that region you have a lot of subduction going on. And if you look in the other side, you have Japanese region where you have again, which is very much prone to earthquake and all those events. So the Asia Pacific region, it is very much seismically active because of this ongoing plate movement and all. So almost 70% of the world's earthquake you find it in these regions. In US, the Dash earthquake with magnitude 7.9 moved the fault by 18 feet and the pipeline above the ground did not face any kind of damage. I'm again pinpointing this question because it's a very good example of the mitigation measures that the people took. So this is a, like, if even if they don't ask you this direct question, and if people if they tell you to give an example of a good mitigation measure, this is a very good one. So which fault or which earthquake? There was a very good example for this. They had this oil pipeline they wanted to build, and they built it in such a way that like it was along the fault, and because of which, even when an earthquake of such a high magnitude struck, it did not cause any problem for the pipeline. So just give me the name of that fault. So I'm giving you the options here: San Andreas fault, Hayward fault, Denali fault, Palu fault. Does something like seem familiar to you, or I have told like what they have done. So if you can just remember the name. Yes, yes. Thank you. So the answer is Denali fault. So as I said, what they did is they built this pipeline along the fault. Why they are making it along the fault? So because if you have the fault plane is like this, okay, and this is the other side. If they had made the pipeline in this direction, okay, so what will happen when the fault movement happens? This pipeline is going to get affected. It is going to get deformed. But if they make it along the fault, like in this way, so when the movement is happening, it is also moving along with that. So as a result, that pipeline will not be affected. So they used a very good mitigation measure while building that entire pipeline. Now the next question is: a flash flood is a flood that options are is caused by heavy rain rather than from the flooding of a river, occurs in urban areas, occurs suddenly or unexpectedly and for a short duration, is caused by the blocking of drains. So what is the definition of a flash flood? Which one? I didn't hear your. Can you put it in the chat box? Then I can see. Okay. So, like I understand. Uh, does anybody of you want to give me the answer? Okay. So, like I understand why you gave the option as A, because it is caused by heavy rain. That is true. Like I don't deny that. But flash flood, like why you are saying it as a flash flood is because it occurs suddenly or unexpectedly and for a short duration. Because heavy rain flood that can stay for a longer period also. But flash flood is something which happens very instantaneously. like because of a cloud burst or something like that, all of a sudden it will happen, and it will happen for a short duration, unlike the normal other floods that are caused by continuous rain and all. So the answer for this is C, occurs suddenly or unexpectedly and for a very short duration. Like the flash term itself tells you that, right? Something is happening very suddenly and for a short duration. So this brings us to the next question. In some volcanic eruptions, mud flows resulted because of snow cover. They are termed as landslide, debris flow, lahar flow, snow mud flow. I think in this week's lecture also they might have mentioned this, but this was also discussed in the previous weeks, I think. Mud flow is basically what? It's a kind of this mass movement in which you have a lot of mud material which flows really quickly. That's basically what a flow says. Okay, so it comes in very quickly. So when this mud flow, as a result of melting of snow cover in volcanic eruptions, what do you call it? Okay. Any other? Lahar flow. Yes. So as Anandraj has said, the answer is lahar flow. So the idea is this, if you have a volcanic mountain over here and it is snow capped, okay, like we have the snow over here. So when the volcano erupts, very hot lava is coming. So this snow will, by default, it will melt, and along with this, what will happen? You have other materials also along this mountain, right? So that will it will bring those materials in. So such mud flows which are associated with the volcanic eruptions and melting of snow cover, we call them as lahar flow. I might have showed you a video, I don't remember, or rather, it might be in the upcoming weeks. So, I'll show you a very good video of mud flow, like how quickly it happens and how far it goes. So, we'll discuss it eventually. Then, the location of maximum damage caused due to an earthquake is at. This I had mentioned in one of the previous questions also. Where do you find the maximum damage? While discussing the zonation, I think. You know how we determine the location of earthquake, right? By triangulation method. No, like I'm not asking about a particular region. Like main central thrust is no. I'm not like I'm asking generally. Like in terms of any earthquake, where will you find the most like earthquake occurs? Let's say an earthquake originates over here, right? And then the energy dissipates in all kind of directions, like this. So let's say the earthquake effect is felt till this. So from here, from this portion till this portion, where will you, uh, see the maximum damage? Main central thrust is basically a fault. Uh, like, of course, earthquakes happen there, but that is not what I'm asking. This is the point of what do you call the point of origin of an earthquake on the surface? Anybody? Just put it in the chat. I'll look at it. The region on the earth's surface where the like basically the earthquake originates within the earth, but directly above. So that point, we have a point on the surface. What do you call that point as for an earthquake? You know the answer, I'm sure, but I'm just trying to make you give me the answer. That's it. The point, let's say, um, this is the fault line. The earthquake originated here. So I'll give you the term for this. So this region, you call it as focus or hypocenter, right? So the point directly above, what do you call it as? This is what I'm asking. Yes. So as Toisna has given, the answer is epicenter. Okay. So now what I'm asking is, this is the epicenter. So epicenter is here, and this is the entire region where that earthquake is felt. So let's say you are like, for a person standing near the epicenter and a person who is standing somewhere like say 100 kilometer away from the epicenter. So who will feel the effect most? Like the effect of that earthquake, like maximum damage, where will it happen? In point A, let's say this one close to epicenter is A and this one close to epicenter is B. So A or B, which region will experience maximum effect, maximum damage? In terms of A or B, you can just give me the answer. Is it A or is it B? Yes. So the answer is A, because it's very close to the like epicenter, means that is the region where that energy dissipation is felt very much compared to, because as it travels that energy is going to dissipate, but here, like that fresh whatever energy is released, these people are going to face. Tectonic plates are essentially what regions of the earth? Inert or aseismic, active or mobile, oldest or mobile, recent active. Out of these options, how would you classify the tectonic plates? Inert means they are just, standing still. Seismic means there is no seismic activity involved. Active means they are moving, like something is going on, and then mobile, that is they are moving. Oldest immobile, as the name suggests, it is old and it is not moving. Yes, it's not inert as seismic, because all the seismicity is happening along the plate boundaries. So tectonic plates have a large role in that. So that is, the answer is active or mobile, because these tectonic plates, that's how you rule it out. So inert or aseismic is what? There is no kind of seismicity happening. But tectonic plates are those regions in the earth where you actually find this seismicity, right? Along the plate boundaries and all. Active and mobile is the answer, because they move. You don't feel the movement. For a person standing here, they will not understand the movement, because the movement is in like centimeter scale in a year. So you won't see in a year, but maybe in a span of like say 100 or 1000 years, you will see the effective movement. So they are active or mobile. Isoseismal denotes contour or line on a map showing an area experienced what? So I'm giving you the options. Similar arrival time of an earthquake, similar earthquake intensity, similar P wave velocity, similar damage pattern. So you have a map, it might have such lines, or rather contour lines. We call these as contour lines. So that is, yeah. So the answer is similar earthquake intensity. So from the name itself, you can actually make a guess, right? ISO means something is same. Seismal is related to earthquake. So that is earthquake intensity. In the Indo-Gangetic plain, the major devastation during an earthquake will be from liquefaction, active faults, tsunami, lahars. Which will cause the maximum damage? You have to remember where the Indo-Gangetic plain is, and all these things you have to just recollect. What liquefaction is, active faults, yeah, and tsunami, lahars. Definitely, you can be sure that lahars is not going to affect, right? And Indo-Gangetic plain, the tsunami effect will not be very pronounced because it's almost so like very away from the coast. It will be there if it's a very, yeah, high kind of thing. So the answer, as you've given, is liquefaction. So see, active faults are present in the Himalayan chain. So there, uh, because of which, that entire region is prone to earthquakes. And because of these earthquakes, Indo-Gangetic plain is basically filled with the sand material. Okay, it is an alluvial plain. You say alluvial is basically the material which the rivers bring. So you, if you remember the example of the Mexico City, so the Indo-Gangetic plain is largely made up of such soft material. So because of that, if any kind of earthquake happens in that area, nearby area, which is due to the active faults in the Himalayas, so what will happen is that liquefaction will happen. Like the risk of liquefaction is more in the Indo-Gangetic plain. Next question. In the thrust faulting, dash move over the dash in an ongoing deformation. So these are the options: hanging wall, footwall, hanging wall, like the order. So you have to tell me what moves over the other when you say it is a thrust fault. Thrust fault is a low angle reverse fault. So I'm giving you a clue. It is a type of reverse fault. So what happens during a reverse fault? Yes, the answer is option A, hanging wall, footwall. The one you told me, like the footwall, hanging wall, that is known as the normal fault. So if you have a region like this, and if this region goes up and this region goes down, this is your hanging wall, this is your footwall. So this is a reverse fault or a thrust fault. At the same time, if you have, let's say, a footwall which is moving up relative to the, this is the footwall and this is your hanging wall. Okay, so this footwall is moving up uh, relative to the hanging wall. This is called a normal fault. This distinction, like please keep in mind, because sir has also discussed, and this is a very basic thing. Like this movement. So reverse fault is in the one in which hanging wall moves up, and normal fault is the one in which footwall moves up or hanging wall goes down, whichever way you can remember it. But this is how the movement happens. The next one is seismic microzonation is done on the basis of computed peak ground acceleration, which in turn depends on. The answer I had already discussed in another question, so even without the options, you can tell me. There is a factor on which the peak ground acceleration depends. This is basically the same question, but I have put it in a different way. I hope you know what peak ground acceleration is. So if you know what peak ground acceleration is, you can tell me. What does it depend on? Yes. So I was giving you the options, but yeah, your answer is right. Lithology of the area. So peak ground acceleration doesn't, like, magnitude of earthquake is not a huge factor, but the lithology of the area is what determines the peak ground acceleration, and which in turn helps you in doing the micro zonation. So it is the lithology of the area. These are some of the topics which I feel is a bit important. I'm not saying you should leave the other topics, but while studying for your exam, please concentrate on these ones anyway, because these I've seen, like, these are repeated multiple times in your assignments and in the lectures also. So if you keep these in mind, at least you will be able to appear for the exam with some confidence. Dash is a section with no earthquakes have been observed historically, but it is believed that the fault segment is capable of producing earthquakes on the basis of ongoing deformation computed from GPS. I think I have repeated the question again, but yeah, anyway, this also we have discussed in the beginning. Which section has no earthquakes but is prone to earthquakes? Like a possible earthquake is there, chance of earthquake is there. Any guess? As I said, earthquake, yeah. The answer is seismic gap, okay? So the options are seismic prone, rupture. Like I don't think you need the options, but the answer is seismic gap. So even if in the options you see, like you don't know the answer, but the options are given like this. So you know earthquake is involved. So definitely some seismic related term will be there. Of course, rupture is also part of the earthquake terminology, but we'll be focusing on seismic. Then we know something is not happening or some gap is there. So then the answer is seismic gap. So that way also, like, you can eliminate the options and you can give the answer. Okay. The configuration of opposite dipping fault explains the dash which occurred in the Kutch region. I think the order came out weird. Okay, anyway. So you have the options also. Opposite dipping fault is there in the Kutch region, and that opposite dipping fault formed as a result of a particular phenomena. I had discussed this in last two sessions. Yeah, I had shown you an image and all. So one of these four is the reason why you have opposite dipping faults in the Kutch region. Yes, the answer is tectonic inversion. So if you remember, tectonic inversion is what? So if you have a normal fault, that is a result of extension. Okay, so if you are pulling from both sides, that can result in a normal fault. If you are compressing, that is you are pushing from both sides, that is going to result in a reverse fault. That is the normal way how it is happening. But in case of tectonic inversion, what will happen is that such faults, like let's say you have a reverse fault in an area which was formed due to a compression which happened some time back, and it just stayed like that. That fault, reverse fault, got reactivated due to a extensional phenomena. So although extension is attributed to normal fault, but in this particular case, what happened is the extension resulted in the reactivation of the reverse fault, and the compression resulted in the reactivation of a normal fault. So the name itself tells you, right? Something is happening ulta, like inverted. So we call it as tectonic inversion. So I hope that is clear to you. But if you want me to explain, I can do it now or even in the upcoming sessions. So I guess, yeah, that is all. So if you have any question, you can ask me from all these problems. So I have discussed, I think, around 30 questions or so. Do you have any questions from this week or last week? Like, I keep repeating it because I don't want you to hesitate in asking anything. So we have, I guess, three more sessions. No, not three, four more sessions in the upcoming weeks. So any question or any part you want me to repeat from the previous part, anything, like you can just let me know. Then I can prepare your slides accordingly so that it is helpful for you. I just want this session to be adding up to your preparation for the exam, so that you don't have to spend too much time into reading everything from scratch. Sometimes when you see certain topics in the form of a question, then you'll understand what is the importance of that topic. Otherwise you'll be just reading through the material. So that is like, that doesn't create a good preparation way. So that's why I was just recapping the entire 5 weeks uh, worth classes. You have any question? Okay, I'll just stop sharing the. Uh, you can ask me, like, if any question is there, or if you are not able to. Okay, main central thrust. So if you remember, let me see. So main central thrust, main boundary thrust, Himalayan frontal thrust. The thing is, uh, I don't know how to open the whiteboard. Let me just see if I can draw and show you. I'm sorry, I don't know how to do this whiteboard thing. So maybe I'll once again share and show you. That's better. So I have an image. Yeah. So the main central thrust, what it basically is telling you, just look at this image. So you know that if you remember, the Indian plate is pushing, like it collided with the Eurasian plate. And because of the collision, definitely what will happen? Some deformation will happen in this region of collision, and it resulted in the formation of the Himalayan mountain chain. So this is not just a single set of reverse fault that is forming. So when this happened, the main central thrust formed first. So the main central thrust is basically, it is a reverse fault. Okay, so this, you can see the movement also. So this has an upward movement relative to the block next to it. So this formed first, then subsequently you have this, I think this is large late Himalayan crystal. I don't remember what LHC is, but anyway, this is one uh, thrust, that is the main central thrust. Once this was formed, so I think you get the idea. The thrust or MCT is basically a region where you have a reverse faulting, a low angle reverse faulting. So that is the main central thrust. So this formed first. This was followed by the main boundary thrust. Then I don't remember what JMT was. I, like I can check it and tell you. But the main three ones or four ones, you can say, that is the main frontal thrust or the Himalayan frontal thrust, the main boundary thrust, and the main central thrust. This formed first, then this. So as you go from here, so that's why in this question, I think one question I had asked about the age, and this was the youngest, in this question only. So this is the youngest one, the Himalayan frontal thrust or the main frontal thrust. So this formed at a later stage. So in the sense that when that movement was happening, so the fault plane will form along regions of weaknesses, right? So these regions of weaknesses developed at a later stage. So first the main central thrust came, then gradually because of further deformation, the MBT came, main boundary thrust. Then that was followed by the uh, main frontal thrust. I hope it is you're able to understand. If not, I can maybe explain it in much more detail in the upcoming session. I can show you a better image so you can understand it. Is that okay? I hope I was able to clear your doubt or what you were asking me, but okay. Yeah, I'll elaborate on that in the upcoming session. So I can show you better images. This one I just kept it for the sake of that question. So I can tell you about that. Thank you so much. So if you don't have any further questions, we can stop today's session. Thank you so much for patiently listening to me. Okay, thank you. You can leave the session.